Right, so here is the subject. This part is us, we're mathematicians, we're looking at something. So what does this mean? In particular, what does this word special mean? In 1915, Einstein put forward the general theory of relativity. General relativity is it's a very, very beautiful geometrical theory of gravity, of the whole of the universe, and in particular how gravity works in our universe. And in particular also it replaces Newton's theory of gravity completely. It doesn't just modify it, it's philosophically completely different. In general relativity, the distribution of matter in the universe causes the geometry to curve. That's the active, that's matter behaving actively on the geometry. And then the curvature of the geometry affects the matter because freely falling matter follows geodesics in that curved geometry. So that's a one-sentence description of general relativity. We're going to do something much simpler than that. We're going to imagine that there's no gravity. Okay, we're going to imagine that we're in a large, comfortable spaceship a long way away from any matter. We know, in fact, that there are places in the universe called the voids in between the superclusters of galaxies. So galaxies, so stars form galaxies, galaxies form clusters of galaxies, and clusters of galaxies form superclusters of galaxies. It's hard to imagine the size involved. In between these superclusters of galaxies, there are enormous voids where there's almost nothing, so far as we know. So imagine that we are there, and there's essentially no gravity. Would it be true, in that case, that we could still use the Newtonian ideas of space to do our physics? And the answer is no. Even when there's no gravity, you have to throw out completely the sort of, if you like, the common sense ideas of space and time and do something very different. And that's what Einstein did in 1905. He didn't publish special relativity from a mathematician's point of view. He published a paper called On the Electrodynamics of Moving Bodies, but it was what we now think of as special relativity. So that's why it's called special. I don't know when the word special started to be used. It must have been after 1915, I guess, when there was something more general. So that's why it's called special relativity. Now, the most important thing about both special and general relativity, but particularly special relativity, is that it's a geometry. Now, nowadays, what a mathematician means by a geometry goes back to Felix Klein, his paper of 1872. Was it? Just excuse me a minute. Yeah. Klein wrote a paper called Comparative Overview of Recent Geometric Investigations. You may know that in the middle of the 1800s, by the middle of the 1800s, lots of different geometries had been discovered by mathematicians. Not just Euclidean geometry, but affine geometry, projective geometry, spherical geometry, hyperbolic geometry. There were lots of different geometries. And as these geometries appeared in the mathematical imagination, maybe it was a little confusing, right? Suddenly there's not just Euclid, suddenly you've got lots of different geometries. How do they compare with each other? How do we understand? And Klein, in his 1872 paper, said, we take the view, it will help us if we take the view that a geometry is a space, a mathematical space, I don't mean space in the sense of spaceships. I mean space in the sense of something like R4 or the complex numbers, a mathematical space, okay? A mathematical space and a group of transformations. I mean, Klein didn't insist that that's what you have to do. You can still study geometry synthetically or axiomatically or in other different ways. But in order to put them together and to understand how different geometries compare, this is a useful thing to do. So for Euclidean geometry, for plain Euclidean geometry, your space is R2, for example. And your group will be the group, the Euclidean group, it would be rotations, translations, and reflections, okay, which make up the Euclidean group. And then you study your geometry by asking questions about objects in the space, so triangles and circles and straight lines in R2, which have, and you're looking for the properties which do not change when you use an element of your group of transformations. So that's what Klein gave us, that view of geometry, and that's how I'm going to approach special relativity. We want a mathematical space, and we're going to want a group of transformations. Now, it's sort of very familiar to mathematicians that when you're studying an object, I mean, you don't always have to, when you're solving a mathematical problem, I'm not saying you always have to choose some coordinates and then do lots of calculations in those coordinates. Sometimes, quite often, you use a different sort of mathematical thinking. You use purely geometrical thinking or some group theory or some topology or something. So I'm not saying that you always use coordinates, but quite often we do solve problems by choosing a coordinate system and then doing some calculations in those coordinates. And we all know that what we're interested in is the things that don't depend on which coordinate system we chose, right? For example, if we're looking for the properties of an ellipse, all right, we might initially write down the equation of the ellipse in that coordinate system, and then it would be a mess. So we choose to move the coordinates, to translate and rotate, to put them symmetrically onto the ellipse, and then the problem becomes much simpler. But the properties that we're interested in, for example, the eccentricity of the ellipse, don't depend on the coordinate system. We could have worked out the eccentricity using this coordinate system. Okay? So there are intrinsic properties that we're interested in which don't depend on the coordinate system. This might also, now what we're going to do, one of the most important revolutionary features of special relativity is that time is included in the structure. So before special relativity, space and time were kept apart. Time was regarded as being there, independent of space. As I said, one of the most dramatic and revolutionary ideas that Einstein gave us was that that's wrong. Time actually has to come in with space. Okay, so we're going to be so our mathematical space here is actually going to be space-time. Some people like to put a hyphen there. I don't mind. I can't. It just uses up a little bit more chalk, so I won't. So initially, space-time as a mathematical space is R4 because it's one dimension of time and 3 of space. And so that's already solved, in a sense. That's already answered the question of what the mathematical space is for our geometry. It's going to be R4. Of course, until we know what the group is, that has almost no content at all. We'll come to the group. What I'm going to be interested in, of course, what we could do is we could, the obvious transformations that we're going to be interested in are still the rotations in space, the translations in space, also reflections, and also translations in time. So we're going to be, of course, we're going to be using all of those transformations in our group. But there's another type of transformation that we're also going to want. We're going to want to consider the situation where you've got two frames of reference, two coordinate systems, which are moving with respect to each other. Right? So if you like, and this is actually a good aid to your imagination, we're not just in one comfortable spaceship, we're in two of them. Okay, we divide ourselves down the middle here somewhere, right? And you lot have got one spaceship and you're in a different spaceship. And you're moving, and the spaceships are identical, and you've got identical measuring equipment on those spaceships. And you're moving relative to each other. And it's that transformation which we want to study. And it's going to reveal some bizarre things to us. So what will the coordinate systems look like? So I'm going to draw a picture of two coordinate systems. This one is S, and this one is S dashed. And this is X, Y, and Z. And so this is one coordinate system. So this is one of the spaceships. And also we need to have a clock associated with this spaceship. So I'll just put a little T there inside a circle, which reminds you that it's a clock, actually, measuring time. I can't draw time as an axis, I'm afraid, so you just have to see it as a little clock here. So there's another frame of reference here, which is Y dashed, X dashed, and Z dashed. And it's got a clock, T dashed, whoops, that's not very good, T dashed. So we've got these, so this is one of the spaceships and this is another one. And we've arranged things so that this spaceship is moving with a constant velocity v along the x-axis of this spaceship. And it's lined up so that this spaceship's x-axis, the x-dashed axis, is the same as the x-axis. They lie one on top of the other. The y-axes are parallel and stay parallel. There's no rotation. And the z and z-dashed axes are parallel and stay parallel. And if you wind back, when the two coordinate systems coincided, then you start both of the clocks at 0. So when t equals 0, t dashed equals 0, and all of these coordinates are identical to these. And then this spaceship moves with constant velocity in that direction. So that simplifies all of the mathematics, because basically what we've done is we've taken a four-dimensional problem, x, y, z, t, and we've made two of the space dimensions sort of passengers. They're not doing anything. All of the action happens in this one space dimension, and as we will see, it happens in the time dimension as well. Now this configuration of two frames of reference, two coordinate, so the two phrases, a frame of reference is what a physicist calls a coordinate system. Okay, it's the same thing. So we've got two frames of reference in this particular arrangement, and we're going to use it a lot in these lectures, and it's called the standard configuration. Okay, let me just glance. Now what I'm going to do, I'll do a few more moments and then I'll pause for questions, but I'll do just a little bit more first. So my question is, what do you think? So suppose you didn't know anything about relativity at all. I suspect some of you do know something about relativity, but suppose you don't, right? And you'd never heard of Einstein. Maybe it's not 2022, maybe it's 1872 or something. And I was giving this lecture, of course it wouldn't be called special relativity, it would be called something else. And I said, here's a setup. What's the transformation between these two frames of reference? Well, I think you would probably say, well, surely t dashed is equal to t. Surely. And then you'd say x dashed is the same as x, but you have to allow for the fact that it's moving, so it's x minus vt. Okay? And then you'd say y dashed is equal to y, and z dashed is equal to z. I think that's what you would regard as the sort of obvious transformation between these two. It's wrong, but we didn't know that until 1905. These two turn out to be right. These two are correct, but these two are wrong. And we're going to find out how, why. You can write that as a transformation, of course, by writing it like this. T, x, y, z maps to t dashed x minus vt, sorry, t x minus vt yz. So that's the same thing written out as a transformation. And when you write it like that or like that, it's called the Galilean transformation. So I've just been asked, well, first of all I was asked, does this phrase refer to this transformation? And the answer is no. I'm sorry, I've organized my blackboard badly. These transformations are called the Galilean transformation. This is a more general thing. This is just a configuration of two coordinate systems. It doesn't imply necessarily any transformation equations between them. That we have to work out separately. I was asked, what is a non-standard configuration, which is a good question. So a non-standard one would be So what we've done for this is we've lined our spaceships up. We've got two spaceships. We've lined them up so that they're both pointing in the same direction. And each spaceship has got an X, Y, and a Z axis, and they've got identical clocks. And they were absolutely side by side when the two clocks read 0. And then at that instant, one spaceship moved off with velocity v, lined up with the first one. That's the standard configuration. Any other configuration, non-standard, would be if the two spacecraft are just doing something, moving with respect to each other, but not lined up in this way. What would happen is that you can get a non-standard configuration to a standard one by doing translations and rotations, you see. And then you ask the question, what would be the Galilean transformation for the translation part and the rotation part? Well, it would be only a translation and a Euclidean translation and rotation on these on the XY XYZ coordinates. Okay, so any non-standard configuration of the two spaceships, you can use Euclidean motions to get it into a standard configuration. Good, thank you. Anything else? Okay, so that's the Galilean transformation, which was it's named for Galileo. Of course, he didn't write it down like this, although he knew implicitly that these were the equations that he was using. And it was used throughout all of the Newtonian mechanics and so on. That's what people did. They used this transformation. One other thing I meant to say about frames of reference in both in Newtonian mechanics and in special relativity, I hinted at it when I was drawing this picture, but I didn't say it carefully enough. The frames of reference must not be accelerating. In other words, a frame of reference must have the property that if there's a free particle observed by that frame of reference, it will obey Newton's first law. It will move with constant velocity in a straight line, okay? Which doesn't happen if the frame of reference is accelerating. So these frames of reference in this standard configuration are going to be non-accelerating. They're called, where shall I put this? I'll start over here. They're called inertial frames. Inertial frames in the standard configuration. And that's what we're going to be using. I should have emphasized that more when I set this up. Okay, the first exercise, which is a very easy one, is to show that these transformations form a group. It's sort of almost obvious. If you're good at group theory, it's sort of very obvious. But anyway, just check in your mind that you know how to do that. And if not, I've got some hints in the solutions. So you could have regarded the Newtonian mechanics as taking place in a geometry, and the geometry would be R cross R3, because it's time and space considered separately, and the group would be the product of the translation group on the R bit, which is the time bit, and the Galilean group on the beg your pardon, it would be the Galilean group on the space. That's what it would be. But people didn't really think of this in those terms then. Okay, next thing that happens, well, actually it had already happened. Another thing that was yes, composition, under composition. I'm sorry, I should have said under composition they form a group, yes. I didn't tell you what the group actually, under composition of transformations. Okay, so Now, meanwhile, we've had Klein talking about how we should look at geometry. Just before that, 1864, we had Maxwell giving us the equations of electromagnetism. Okay, so electromagnetism. So he wrote down what we now call Maxwell's equations, and in particular, these equations describe the behavior of light. And when this was first written down, light was, of course, it has a dual aspect. It can be thought of as a particle or as a wave. But certainly the obvious interpretation from the point of view of Maxwell's equations is that it looks like a wave. And so the question was, what is the medium which is waving? Something is waving, right, in light. So what is it that's waving? And so people imagined that there was a medium called the ether, which was the thing that was fluctuating for the light waves. But this turned into a huge problem. And I'm coming forward now to 1887. There's an experiment. In fact, this wasn't the only indication that there was a problem, but it's one of the most well-known ones. An experiment by Michelson and Morley, who first people to ask it. They said, okay, light travels at a specific velocity, which we refer to as c. I'll tell you what it is. It's a large number. And if there's an ether, then it's traveling with that high velocity through the ether. Okay? So where is this ether? Well, it must be all around us. And in particular, it must be all through the solar system. Now, the Earth in its orbit around the Sun, I mean, it's hard for us to move here on the surface of the Earth. It's quite hard for us to move at a speed which is anything like as fast as light. Light is so fast that everything we do is just pathetic in comparison. Okay, but the Earth itself in its orbit, let me get the figure right, 29 kilometers per second. So 1 second, 2 seconds, each of those we're traveling at through 29 kilometers in the orbit around the Sun. So that's pretty fast. The speed of light is about 300,000 kilometers per second. We're 29, so it's a bit smaller, but maybe it's measurable. In particular, you see, if the Earth is moving through the ether, then sometimes the Earth would be moving in one direction through the ether, and then in the, you see, there would be the velocity that you measure for light ought to be a bit different, right? It would be the velocity of light in the ether either plus or minus the velocity of the Earth through the ether, right? That you'd have to do a, or it may be that so what they did was they built an interferometer. I don't pretend to understand all of the physics of interferometry, but basically you split a beam of light here and you send some of it along there to that mirror and it comes back, and the other part goes along to that mirror and it comes back, and when the two signals return they interfere with each other, and it's an accurate way of comparing the time it takes for light to go out and back along here with the time it takes for light to go out and back along here. And they built one of these things. It was well within technical ability of 1887. And you can move it around so that this might be the direction in which the planet is orbiting, and this is at right angles to that. So there should be a difference, okay, in the travel times. And then you can change it around and fiddle about and experiment. And the accuracy of their equipment was easily enough to detect the predicted difference in the travel times. And whatever they did, they detected no difference, right, in the travel times. So the velocity of light was absolutely the same in either direction. So the velocity of the Earth through the ether of the solar system was just not detectable. So this was a puzzle. People were certain that there was an ether, so they didn't give up the ether yet. That's what Einstein did, basically. But it was an extremely strange situation. By the way, I've got another exercise here, which you might find amusing. It's just for you to check what the difference is in the travel times here. So in my exercise, I just imagine that there's a bee. You know, I don't know what the Turkish word for bee is. It's a little buzzing insect. Bzzz, okay, a bee. You got it? Say again? I do. Okay, right. It's one of those. And it's flying. In the exercise, you'll see it's flying from a point P to a point Q. So it flies there, and then it flies back again. So it's just like one of the pieces of the interferometer experiment. And the first one day it does it, and the bee's airspeed is v. And on the first day, there's a wind blowing. It's a windy day, and the wind is blowing with little, so that's a big V, and that's the wind blowing, little v, okay? And you can calculate using almost school mathematics how long it will take the bee to go there and back. You have to put so you say the distance is d or something. Then then the bee comes home, has a rest. Next day, he wants to go off to this flower again because it was delicious. But the next day, the wind has changed, and it's now blowing in that direction. Same velocity, same strength. And again, you can calculate how the bee does it and how long it takes and so on. And you'll get two different answers. And that's exactly what this interferometry experiment failed to measure. If there is an ether, then unless somehow the Earth is carrying the ether with it, and why should we do that? We ought to be able to measure this, but we didn't. So this was very puzzling. So I'll say a couple more things and then I'll pause again for questions. So Einstein was fully aware of this puzzle. In particular, he was also fully aware that the Maxwell's equations for electromagnetism do not transform correctly under this transformation. Okay. And so somehow he was uncomfortable with the fact that you've got these beautiful equations for electromagnetism, Maxwell's equations, and in a separate piece of physics you've got this Galilean transformation which works for all of mechanics very well. Newtonian mechanics is amazing, okay? So you appear to have two bits of physics that don't fit together. And this was really a challenge. This was the challenge that Einstein rose to. He felt that, no, there aren't two physicses, there's one. We've got to work out how to. So what he did was he adopted two principles, and I'll just write them down and then I'll pause for questions. So the first principle basically says there's no ether. He didn't say it like that. So I'm going to refer to it as special relativity 1. All inertial frames these things are equivalent for all physical experiments. And that immediately discards the ether, because the ether was a special reference frame, right? And this says there is no special reference frame. So in particular, there's no ether, okay? All inertial frames are absolutely equivalent, whether you're talking about mechanics or electromagnetism or anything else, actually. And the second principle that he adopted was light has the same velocity in all inertial frames. You can argue that he's adopting as a principle the experimental result of Michelson and Morley. I think he was more concerned with pulling physics together, actually, but in effect he was adopting that experimental result as a principle. It doesn't take you very long when you look at these and you're thinking about looking at the standard configuration and so on, you very quickly realize that those two statements will destroy this, okay? Because if light has the same velocity in this frame as it does in this one, then this can't be right. It just can't be right. Einstein knew that he was wiping out hundreds of years of physics, essentially. It was a very, very brave thing to do. What we're going to do after the break is start to find out how to deduce from these two principles what the correct transformation should be. And in particular, we're going to find out that this is wrong. In other words, time is inevitably tangled up with space, which was completely revolutionary, right, in 1905. But before then, let me make a few more remarks, really just about the idea of transformations and so on. It's sort of clear, isn't it, that the apparent, and I emphasize the word apparent, the apparent length of this piece of chalk is not of any physical significance. All you can see is just a little white disk. All you can see is just its apparent length is, but doesn't really have an apparent. As to me, I can see the whole thing, right? Or we could switch and I could say, right, now, to me that just looks like a little white disk. Length, I can't even see its length. Let's call its apparent length 0. You say, no, it's not, right? Now, so the apparent length is not a useful thing to talk about. The actual length, which is invariant under rotations and translations, as you can see, the actual length is an invariant. It is a physical property which might, in some cases, be useful to talk about. And that's what we're going to do after we've worked out what the correct group of transformations is going to be. We're going to find what are the things which are invariant under the new transformations. And we're going to discover, and this is the bit that's always shocking and which I think what attracts people to special relativity, we're going to discover that some things that we thought were invariant are not. And in particular, the length of a piece of chalk is not invariant under the new transformation. So we're going to have to abandon some of our ideas in favour of new ones. Okay, now there's one thing that I can do actually even before we write down the group of transformations. One of the things we're going to have to abandon is simultaneity. So I'll do that and then we will simultaneously have a break. So in Newtonian physics, under the Galilean group, time, remember, in that type of physics is just a bystander. It's a passenger. It doesn't get involved. Which means that if I think two events, then so will everybody else. We will all agree, however fast we are moving, however far apart we are, whether we're upside down in New Zealand, doesn't matter. We'll all agree if two events are simultaneous. And if they're not simultaneous, one happens before the other one. Okay. So in Newtonian physics, there was this belief that simultaneity was something which was invariant. Everybody agreed on it. But in special relativity, it's not. And you can see that straight away if you imagine an aeroplane. I'll try and draw one. So here we are. And it's got a bigger wing than that, hasn't it? It's got an engine thing here, and it's got right. So there's an aeroplane, and it's flying above us here. Us. Okay, flying along. Now, in the middle of the cabin, so you've got a passenger in the front row, and you've got a passenger in the back row, not a good place to be, and you've got one in the middle, okay? And in the middle of the cabin, you imagine that somebody takes a photograph, and there's a flash. So in the middle of the cabin, there's a flash of light. And if you're on the aircraft, in fact, there it is. You can hear it. Okay, it's up there now. So if you're in the aircraft, you would argue that if it really is exactly in the middle, the passenger at the back will see the flash of light simultaneously with the passenger at the front. In other words, those two events, namely this passenger seeing the flash and that passenger seeing the flash, will be simultaneous events. Now, what do we think? Okay. For us, that flash moves in that direction and in that direction at the same velocity, c. It doesn't move in that direction with c plus the velocity of the aircraft. It moves in that direction for us with velocity c. And it also moves in that direction, not with velocity c minus v, but with velocity c. So that's how we think of that flash of light. But for us, this passenger is moving towards the flash of light, and this passenger is moving away from the flash of light. So this passenger will certainly see the flash of light first before this one. So for us, those two events, namely when these two passengers see the flash of light, are not simultaneous. There's no escape from that. Once you adopt this and this, there's no escape. There is no such thing as, well, there is simultaneity, but it depends on who you're asking. Okay? It depends on the observer. simultaneity is dependent on the frame of reference. If you've got two different frames of reference moving with respect to each other, they will disagree about simultaneity.